know in your homework you're going to have to grapple with third order. Over the course of chapters 4 and 6, you might even get a fourth order. If I'm not mistaken, one of the chapter 6 problems has me do a Wronskian check for 4 functions. All right, so let's do the Wronskian check for the 3. So if we have 3 functions, the Wronskian grows. And the math we're doing, so this is the Wronskian if we have 3 separate functions, okay? 3 different functions equals. And it still starts with the functions in the top row. So that's now going to be y1, y2, y3. And then the absolute value notation doesn't mean to make things positive. That's linear algebra or calculus 3 notation for determinant function evolving. And in order to do this cross-multiply process for higher numbers of functions, the size of the grid has to be a square. So right now we have 3 functions in the top row. So below that we need 2 more rows of stuff. So the second row is going to be the primes. And then the second derivatives are going to go in the third row. Holy cow. So the second row is going to have the first derivatives. And the third row is going to have the second derivatives. And the derivatives in the Wronskian, they go up to, but not including the highest derivative in the equation. So the equation is third order. This is going to stop at the second derivative. Does that make sense? All right. So let me write down what that's going to look like for this case. The order that you put these in here doesn't matter, actually, by the way. So I'll put them in the order I see them. So we're going to try to do the Wronskian of e to the negative x, cosine x, sine x. I. Equals. Top row, all 3 functions just get written down. Second row, all of their derivatives. Sine x, and then this derivative is positive cosine x. And then the next row is all of their derivatives. Positive
Yes.
x, negative cos. By the way, do you realize these are the same derivatives we just computed when we were checking that? So normally how this is going to go in your real math life, whatever that is if you're the one who found YH, you're not going to check it properly because you're the one who found it. You know it's right. So you won't necessarily be doing the same math twice in a row like we are. All right, and then the question is, how the bleep do we compute this? So let me say I have been debating this, every so often since yesterday. So what we're computing here, in the case that we're checking 3 functions for independence, so this is called a 3x3 determinant. And if you have previous linear algebra experience, if you're in linear algebra this semester, this is chapter 3 and we haven't quite gotten there yet. The math we're doing, you can think of this as the cross product if you're in calculus 3. We use that same notation. If you have linear algebra experience, it's called a determinant, whatever. I'm going to tell you because like for differential equations, the thinking is that you're going to be engineering nerds, something like that. I'm going to show you the engineer shortcut really quickly though. I forgot about time. So the engineer's shortcut is in this grid, we still kind of want to do that. So the engineer shortcut is out here. We're going to recopy the first two of these. So e to the negative x, negative e to the negative x, e to the negative x. And then we copy the cosine column. Cosine x, negative sine x, negative cosine x. And then an engineer shows me this and I say, really? That's a shortcut? So tomorrow I may show you the math shortcut, which is really better. And what it is a gigantic cross multiply. So why engineers add in those extra columns is they're kind of like remembering how this goes. So we go this times this times this. So down and to the right. But we actually do 3 separate down and to the right multiplies. So down and to the right plus this plus this. So far, this Wronskian is going to have 3 products of 3 functions. And then we come back the back way and we do 3 subtractions. Different color for the subtraction. So we come the back way and multiply. We got this times this times this.
Oh.
Wait, did I get off kilter? No, I think I'm good. Minus this times this times this. And if I played my cards right, we're going to end up in this corner. This times this times this. So we have 3 pluses and 3 subtractions.
That's not really a shortcut.
I don't think so either. Tell that to Mr. Long, the engineer. And I'll show you a math way tomorrow. So there are different properties that the determinant has that you would learn about in linear algebra. If you have any knowledge of the determinant that you've picked up in the streets or you've had a class. Where
You picked up in the streets.
What's up, bro?
I don't know what streets those are. Maybe you've been walking around town.
That's a real story.
If you've been walking around.
So you're free to use whatever fun facts you know about.
You picked up on the street.
But for now, that's how it's going to go. And just be grateful for now, it's not 4 functions. Because there's no shortcut like that, even though that's not a shortcut. For the 4 function check, we really do have to do a lot of math for that.
So there's no shortcut.
Yeah, there's like the last dimension in which there's a shortcut is 3. And engineers say, fine, I live in 3D, that's all I need. But the math can go into higher orders, and the determinant becomes much more complicated.
Oh, Lord.
All right. And just be ready. I know there's a homework problem on that sheet somewhere that's 4 functions.
Professor, are we ending class early?
Are we what?
Ending class early today?
We are ending class right now. So that clock says it's time. No!
We got like 30 more minutes.
No, we're not. Thank you very much. We can't fail.
Professor.
You
like
need an escort out
kids.
of class because we almost got out 20 minutes early. Yeah.
So for like if we keep going, we're still gonna do that same thing, right? You just copy the first column.
No, that the
You can't
short, this
Do I look like
shortcut
Vanessa to you?
does not work if you have 4
Fuck, Jordan.
functions and the functions and their first 3 derivatives. There is no shortcut for that. There's a long cut, which is actually the
So a long cut?
definition of the determinant. So when that time comes, which won't be until a later chapter 6, it's somewhere on that sheet, we'll worry about it then. Yes.
So I have a question.
Yes.
So right now what we've done so far is like checking if the answers are right,
Yes.
basically. So how
Yes.
do we figure out the answer?
That's the real question. So that's, I think, verifying the answers are right. That's section 4.1. We have 3 little problems about that. The whole rest of the sheet is how do we come up with the answer our own dang self.
So
So I think, I don't know that that's the optimal one. But I'm gonna try that one. You may or may not like this. I'm gonna try to, help us see if we can come up with the solutions to that third one. This is a bit premature, but that's okay.
How did we become a third order derivative?
Say that again?
How did we become a third order derivative?
It's third order, so you say you drop
It
the
goes, so because the third order derivative is gonna be governed by the first three. So the value for this is gonna depend on those three. So the issue is, are those three each contributing something new to the mix? But from a practical point of view, that Wronskian check, it has to be squared. So if we have three things we're checking, we have to stop at the second derivative.
So n minus 1 times n.
It's like one less than the order, yeah. I don't really want to solve one of these today. Let me give you, whatever. They paid me for it. Let's do it. So for this kind of equation, and this got me into a lot of trouble, not so much in math. I don't really remember learning this in math. I know I did, but I don't remember. I remember in physics, when I started taking like the upper division physics classes at Cal State, East Bay or something like that, I would be sitting in my physics class, and it was a physics class, but they were doing math, like they were doing this kind of math. And in physics, they would take a differential equation, say like this, and say something like, assume that the solution has the form of an exponential. This is the kind of thing they would say. And I'm coming in there with my pure math background, like I want to see a derivation. I want to see you do some fancy footwork and explain where that came from. And I got, brought down a peg or two several times by the person saying, the physics teacher saying, first of all, what's this old lady doing in my class? And then basically just shut up and we're gonna check it and you're gonna see why it works. Like, we're gonna try this and we're gonna somehow get that that's gonna produce those three answers over there. And their attitude was kind of like this, which is gonna be our attitude in here. We're gonna assume a solution of a particular form and we're gonna see if we can actually pony up the right answer from that assumption. If we can't get those three answers from this, that means the assumption is wrong. And I go back to Cal State paper and I say to all those physics teachers, in your face, you can't do this one. But this is gonna work for this one. I'll explain why later. So what we're gonna try to do here is I'm giving us an assumption for the solution, which is that the solution is exponential. Now really, two of our solutions are trig, so I don't really know how that's gonna work out. But here's how my arm got twisted when I learned this in physics. The teacher says to me, look, they always start, look, we're trying to find a function whose derivative and second derivative and third derivative, they can all cancel each other, is how they would talk. And they would say, so what that means is whatever we think the y is, if we keep deriving it, we keep getting the same type of function in such a way that when we add all these together, we get 0. And then they would look me in the eye, like put me on the hot seat, because I asked the question, what kind of function is its own derivative? Exponential. And all we do is we leave a little wiggle room to adjust the number and the power. Maybe it's exponential growth, maybe it's exponential decay, maybe it's faster growth or slower decay or what have you. So we start with this template and we're going to try to force it to work. That's how they do it in physics, that's all I know.
Wouldn't like a trig also do that?
So in the real solution, in the actual solution, there is trig showing, but that trig, weirdly, is going to come out of this, very strangely. So here's how they would go in physics. So they would say, we're going to assume this is how the solution looks, and we're going to try to find out what the R should be. So looking at our actual solution, what is one of the R values?
Mhm.
So comparing that to this, so which of our solutions fits this template?
You sign it?
Which of those three?
One.
E to the negative x? So one of the solutions from this is gonna be r equals -1. And then for the trig, we'll just see how it goes. Maybe now we won't have time. So what we're gonna do is we're gonna take this assumption for the solution and try to sub it in and see if we can deduce what the r needs to be. So we're gonna sub this into the DE, sub this assumption into the DE. Okay, so I'm gonna start on the back end, 0. What are we assuming for y? E to the rx.
Mhm.
So you know how you were kind of upset with me, because our, kind of very upset with me that our test didn't have a lot of numbers, it was all symbolic? One of the reasons I was thinking of was this. What's symbolically, what's the derivative of e to the rx?
R E to the R.
R e to the rx.
Mhm.
What's the derivative of that?
R squared.
R squared.
E to the R.
We're at the end though. R cubed. E to the rx. All right, and then I look at that and it gives me a little headache or makes me dizzy or something. And I'm like, wait, what am I trying to do? I'm trying to see if I can figure out what the r should be. Factor out the e. So if we factor out the e, what we'll have left is r cubed plus r squared plus r
Plus one.
plus 1 equals 0. I stop myself again, and wait, what am I trying to do? I need to figure out the value for r. So the exponential in front of the bracket, that's not going to be 0. So the thing in the bracket has got to equal 0. But I'm still suspicious, kind of like you guys look. Like, I'm still wondering how the bleep, where's the cosine going to come from? So it seems like it came out of left field. So what this assumption does, and this is fairly standard, at least based on as much physics as I've had, that the math that we're doing is to take that Math 292 question and whittle it down to this. So we're taking a problem involving third order differential equation and we're turning it into an algebra question. We give this to our little cousin in pre-calculus
And they can do
and say, all you have to do is factor it.
The cube R squared. Equals -1.
And I even think factor by grouping.
Yeah.
How about these two? R squared, R plus 1, plus R plus 1. I'll put a 1 in front so I don't confuse myself. So we've turned our difficult problem into an algebra problem. But the proof of the pudding is going to be in the eating. Like somehow we're going to have to get this answer. I don't really see how the algebra is going to do that. Did you have a question, Jeremy?
I just said it's -1.
Yes, so that's one of them. So, so the r plus 1 can factor out. And that's going to give us the r equal -1. Okay, so this one is going to say r equals -1.
0.
Okay, so for this one, let me write r squared plus 1 also has to try to be 0.
Imaginary.
Something imaginary. So r
So that's where the
squared,
cosine and sine come in.
-1, r is plus and minus I.
So that's the cosine.
When I do the imaginary I make it sort of a weird handwritten I, so it doesn't look like I hat or current I or something in some other class. All right, so let me write down the solution. This will be a perfect, horrible place to end. So what that's actually trying to tell us, it looks like it's trying to tell us three separate exponentials. So what that math is giving us is, I think we're still going to get C1e to the negative x. The r equal -1, that would be y1 in the solution we were given to test. Okay, and then here comes the bad news. To erase display. So it looks like we're going to have this for the other two, C2e to the positive ix, and then C3 e to the negative ix. And then we ask the question, how does it? So there's the strike against this answer, and we're going to not let this happen to the user of our work, is that answer is not wrong. If you sub that back into the differential equation, it's going to work. But I'm sure you can imagine other people, not us, but other people being alarmed to see the I. Like they're afraid. It has the name imaginary.
How dare you?
And, but it turns out there was this little fun fact. So this is the right answer, but that's the right answer also. And we'll pick up with this tomorrow. There is a vehicle to get us from the answer with the imaginary exponentials into sine and cosine. And the vehicle that gets us there is named after my favorite mathematician.
Euler.
Which who?
Euler.
That's Euler's identity.
That's Euler's identity.
And that's the cosine
Oh my
sine.
God. So calculus 2, Euler's, read that guy. Euler's identity is going to be the vehicle that can take us from an exponential with an imaginary in the power and morph it into sine and cosine.
I have a fun fact for you. Euler actually wanted to call the imaginary number lateral numbers. It makes it easier to understand what's going on.
Oh, that's not bad.
Laterals.
So normally the way when there's imaginaries and reals mixed together, the reals are this one, and the imaginaries are this way. Like you can graph them in the plane. Oh, that's interesting. I still hate him, but that's okay. So think laterally for now. So tomorrow we'll pick up with this, and at some point, I feel that other teachers are doing problems on the board in here, but at some